Okay, yeah, thank you very much for the invitation, yes, to this nice online conference. Okay, so my talk is about birational geometry of Fano threefold weighted complete intersections. And okay, so first, so suppose we are given uni-ruled projective variety V, then one obtains here we have V, no. One obtains modifiable space X over S by first taking non-singular model and then run minimal model program. Yeah, this is very well known. And here we have many choices here. And even if we fix the model, we still have choices in general. So, okay. So first I define this modifiable space X over S, whose total space X is birational to V, is called a birational modifiable space model of V. And by the above choices here, in general, these models are not unique. And I define birational rigidity and solidity. So let X be I call Mori-Fano variety, which simply means Fano variety of Picard number 1 and in the terminal category and Q factorial. Okay, I call this Mori-Fano variety in this talk. And X is birationally rigid if X is unique birational modifiable space model of X, of course up to isomorphism. And X is birationally birigid if it consists of, this model consists of exactly two Mori-Fano variety. So one is X itself and the other is X prime. And this X prime is not isomorphic to X. Okay, this is birigidity. And then we say X is solid here if any such model is a Mori-Fano variety. I mean, X is not birational to a modifiable space over a positive dimensional base. So I don't care about the number of models, but the models are, all models are Mori-Fano varieties. Okay, then so I will talk about the Fano threefold weighted complete intersections, and I begin with a small definition. So let X be a subvariety in some weighted projective space and defined by some equations, homogeneous equations. And we say that it is quasi-smooth if the affine cone defined by the same equation inside the affine space is smooth outside the origin. So this is quasi-smoothness in general. And so we have a famous classification of quasi-smooth Fano threefold weighted complete intersections of index 1. So this means that the class group is isomorphic to Z and is generated by anti-canonical divisor. Okay, index 1. In codimension 1, I mean weighted hypersurface case, there are 95. families, and in codimension 2, we have 85, and in codimension 3, we have unique family, which is the complete intersection of 3 quadrics inside P6. And okay, first of all, this codimension 3 case, this complete intersection is not solid. It is birational to a conic bundle over P2. Sorry. Yes. So from now on, I will talk about the codimension 1 and 2 cases. Yes, so let's consider weighted hypersurfaces. So birational rigidity of 95 families are known. Let me talk about history. So first of all, is the famous result of Iskovsky-Manin. They proved that smooth Kartic threefold is birationally rigid. Okay, and then smooth sextic double solids, which is degree 6 hypersurface inside this space. This is rigid. And then Kortip-Kurikov-Reed proved birational rigidity for 95 families under some assumption, generality assumptions. And then finally, Chertsov-Pak removed these assumptions. So we have very simple result in codimension 1. So any quasi-smooth Fano threefold weighted hypersurface of index 1 is birationally rigid. This is very simple. Then let's go to codimension 2 case. This is slightly involved. So I explain first 3 results. The first, Iskovsky-Pukurikov showed that general complete intersection of quadric and cubic is birationally rigid. Yes, birationally rigid. And then Kortimella showed that the general complete intersection of cubic and Kartic inside this space is birigid. Yes. Another model is Kartic threefold with unique singular point, terminal singular point. The third, Greenenko observed that quasi-smooth complete intersection of 2 cubic inside this space is birational to Delpez fibration of degree 3 over P1. So this is not solid. So we have 3 examples. And after these 3 results, I studied comprehensive studies of the remaining families, 82 families. And consequences that the phenomena occurring to the remaining families are exactly the above 3 cases. But to be rigorous, proofs are not completed yet. So let me explain this. What is done and what is not. So first, I talk about the birationally rigid cases. So, okay, here is theorem. Any quasi-smooth member of each of the specific 18 families is birationally rigid. And together with this X23 case, there are 19 families whose general members are birationally rigid. And here, I have proved this for under some generality assumptions, and Ahmadinejad Zuccon removed these conditions. Okay, so what are the 19 families? It can be characterized in terms of weights and degrees of the defining equations. So although we do not need this kind of things, but we have simple characterization. Okay, so yes, X belongs to the above 19 families if the equations are not equal, and the D2 larger degree, D2 is greater than 2A5, or if it's equal, then it is we have this strict inequality. This is a numerical characterization. Okay. Oh. Okay. So next, I talk about the non-solid cases. So yes. So here is theorem. Any quasi-smooth member of each of the specific 6 families is birational to a Delpech fibration over P1. So it is not solid. So in this case, the characterization of these 6 families is very simple. These are characterized by this equality of the degree of the defining equations. So in this case, I can show how Delpech fibration appears. So, okay. So let's consider this example. X66 in 1, 1, 1, 2, 3, 5 in this space, and let coordinates be x, y, z, t, u, and b. Equations can be written in this way: Vx minus f degree 6 in variables x, y, z, tu, and second equation Vy plus g6 x, y, z, tu. This is equations for x, and eliminate the variable z, and variable b, we have this equation, and consider in 1, 1, 1, 2, 3, And okay, let's write this as Z. Z. We have projection. And here, this Z, from this Z, we consider projection to XY coordinate, P1 projection. And you can see this fiber by putting numbers into some number into X and Y. We see these fibers. Fiber is derivatives of, in this case, degree 1. I mean, degree 6 hypersurface in P1, 1, 2, 3. So we can somehow resolve this indeterminacy, and then we obtain genuine derivatives fibration in this manner. Okay, anyway, for these 6 families, we can conclude they are not solid. So the main objects of this talk are the remaining families. Before going to the remaining families, I quickly recall famous Sarkisov program. Although everybody know this. Okay, so here is the theorem. So it says any birational map between 2 modifiable spaces, x over s and y over t, can be decomposed into a sequence of so-called elementary links in this way. And here, elementary link is suitable special kind of birational map between modifiable space. And in my talk, I only from now on I only consider links from modifiable Fano variety, and in this case, elementary link here from a Fano variety X to some modifiable space is always initiated by extremal divisorial contraction. So I mean, this sigma fits in one of the diagrams. We have X here and divisorial contraction here, and we have flips or flops and some composition of flips flops, and we obtain something y prime, and we have divisorial contraction here to, in this case, Fano variety, or after the composition of flips or flops, we obtain modifiable space over positive dimensional base. Okay, then let's go to the remaining 60 families. Okay, it's not important, but okay, let X be a member of the remaining 60 families. I mean, we have 85 in codimension 2, and this is birational rigid families, and this is non-solid families. So we have remaining 60 families. And then, okay, we have this kind of numerical characterization, which is not important. And yes, in this case, we may, I mean, after coordinate change, we may assume 0, 0, 0, 0, 1 is inside X. this is okay. This is terminal quotient singularity of index A5. Okay, but anyway, we have this point. And basically, in this case, we have another model. Let me explain this. So we have the diagram. Okay, this is elementary link, where the target space X prime is a Fano threefold weighted hypersurface of index 1. But it's not quasi-smooth. And in this diagram, this psi is the Kawamata blow up at the point P. Okay, this is a unique extremal divisorial contraction centered at terminal cyclic quotient singularity. Okay, Kawamata blow up. Okay, anyway, and this psi prime is extremal divisorial contraction to a non-quotient singular point. Of course, terminal singular point. Terminal. Okay, this is, of course, Mori-Fano variety. So we have another model, X prime. And as a remark, so this P prime is the unique non-quotient singular point of X prime. X prime may have several singular points, and this P prime is a unique non-quotient one, and the other ones are all quotient singular point. Okay, and I do not discuss here, but the ambient weighted projective space of X prime and defining equation can be described explicitly. Yes, maybe I will discuss later, but okay. So anyway, we have another model. And so we divide 60 families into several types according to the singularity of this terminal singular point P prime. So let's record the classification of non-quotient terminal singularities. And they consist of the following types. And in a Gorenstein case, we have CA, CD, CE, its hyperplane, general hyperplane section is Duval of type A, D, E, respectively. And in the higher index case, we have CA divided by cyclic group of order M. So I denote it as CA over M, where M can be arbitrary positive integer. And some exceptional case, CA denoted CAX over K. Here, K is 2 or 4. Okay. And we have CD divided by cyclic group of order L. L is 2 or 3. And CE over 2. Anyway, we have this kind of types. And we say, okay, let's go back to the codimension to Fano X. So we say X is of type star. Here, this star is one of this singularity type. So we say X is of type star if the unique non-quotient singular point is of type star. So here you can see the number of families in each type. So we have 60 families total, and in total, and yes, yeah, you can see this table. And okay, I have to record maximal extraction center to explain further. Yeah. So let X be a Morifano variety. And yes, let phi be an extremal divisorial contraction. Here, E denotes the exceptional divisor, and this gamma is image of E, center, yes. And this phi is maximal extraction if there exists a movable linear system M, which is linearly equivalent to minus mkx on X, such that E is a non-canonical place of this pair. So in other words, this inequality holds for the exceptional divisor of contraction. Okay, this is usual discrepancy. And in this case, its center, gamma, is called the maximal center. And this is an important remark. If there exists an elementary link from X, then the divisorial contraction. So I explained that elementary link from Morifano variety always initiated by divisorial contraction. So if there is such link, then the contraction initiating the link is maximal extraction. So okay, I explain strategy to prove birational bi-rigidity for the 60 families. So very simple strategy, very straightforward. Yes. So first, classify maximal extractions of X. And this is first. And the second, to each maximal extraction, observe that the link, elementary link, initiated by the extraction is either a self map or a link to X prime. Something. Can you hear me?
Yes, that's fine.
Yes.
Okay. Thank you. And yes, do the same for X prime. Anyway, classify maximal extractions of X and X prime and the associated link, if there is such extraction, and observe that the link is the target of the link is X or X prime. So this will clearly show that X is birationally bi-rigid. Okay, I finished the preparation, and so I explained what is known so far. So the strategy 1 and 2 are done for all the 60 families. So I mean, the classification of maximal extractions on X is done, and the elementary link from X is completely understood. Here, elementary links from X are classified. They are birational involutions and links to X prime. And okay, so next, so let X be of type this one. Then sorry, these are also done, and bi-rigidity is proved. So yes, this is what is known so far. So the remaining case is the types of families of these types, and there are 25 families. Yes. So because of the time, I cannot explain about the proof in detail for these things. But okay, I quickly explain why theorem one is here. Theorem one can be proved. So basically, we have many machineries to exclude smooth points and curves as maximal center. So mainly by considering intersection numbers. So if we have a maximal center, we have movable linear system vanishing highly along the center. So by intersecting members from this system, we have effective one cycle vanishing along the center at the very high order. So and then we can consider some intersection numbers and derive a contradiction. So in that manner, we can exclude. Yes. And so the difficult part is the exclusion of singular points, or the construction of link centered at the singular point. So, okay, exclusion is doable. Once divisorial contractions are classified, of course, centered at some singular point, classified, and also their explicit descriptions are given. In this case, doable. And so, okay, I need to explain why theorem one. So divisorial contractions to terminal quotient singular point and a point of this type. So these are exactly these ones. Anyway, divisorial contractions to these points are classified in a very explicit manner by Kawamata, Kawakita, and Hayakawa. Yes, and why the remaining cases are left? So first, I have technical reasons for X of types this one. These are also classified, but something slightly complicated. So yeah, maybe I was lazy. So this is one reason. And the essential reason is that the divisorial contraction to a point of type CD and CE are not classified. Yes. Okay, I wrote this one. It's difficult to explain, but actually, these contractions to CDCE are classified according to Hayakawa. I privately communicated Hayakawa, and he said he completed classifications. And I have his private note, but it's not published. So I don't know why. I think it's mathematically correct, but it's not published. So I cannot freely use these classification. Okay, this is why I wrote delicate. Okay. So now I will talk about the new result. So let's consider this one, and which is a member of family of type CD. And the other model, X prime, is a weighted hypersurface of this type, P1, 2, 3, 5, 1, and coordinates are X, Y, Z, T, W. And anyway, the equations is of the form. This is very explicit in terms of equations. Okay, so yes, then the point P prime is the point 0, 0, 0, 0, 1 is the CD point. Okay, and okay, so today's main theorem, I verified completed the proof for this family, one family so far. So yes, this X is birationally bi-rigid. And okay, yes. So let me explain how to prove this result. So yes, let X be as in the theorem, 2 as above. So recall that we have the diagram, elementary link. Yes. From the specific point. And this is, okay. Yes, this psi is Kawamata blow up. And we have flop, and this is divisorial contraction centered at this, anyway, CD point. Yes, let's call this link tau. Okay. So as I explained, elementary links from X are already classified. They are explicitly, they are one birational involution of X, which initiated as a Kawamata blow up at this kind of singular point. But anyway, one birational involution, and this link, only two circuits of links, elementary links. So need to work with this side, X prime. And what we actually prove is the following. So first, okay, no smooth point of X prime is a maximal center. Okay, I skip. Basically, this is done by the usual method. Okay, and okay, then I prove no curve on X prime is a maximal center. Okay, and third, this is the essential difficulty. Yes, this is a difficulty. What I prove is that this divisorial contraction, psi prime, is the unique, okay, divisorial, okay, to be precise, extremal divisorial contraction centered at this point. So I will explain how to achieve this third one. So actually, I have to classify divisorial contractions to this point. And yes, as a step one, divisorial contraction, step one, divisorial contraction to a CD point. This is a general result to a CD point with discrepancy strictly greater than 1 are classified by Yamamoto. So in this particular singularity, I can see that as an application of Yamamoto's classification, there is no such contraction. So step two, so we need to consider the discrepancy one case. So first of all, we already have one divisorial contraction, psi prime. So let E prime be its exceptional divisor. Then the singularity of Y prime along E prime are these points. This can be seen very easily and explicitly. The yes, inside Y prime we have E prime and X prime, and we have P prime. And Y prime has singularity 2 of type this one, and 1 is 3 singular points. So from this, we can conclude the upper bound number of exceptional divisors centered at P with discrepancy 1. Because if there is some okay, sorry. First of all, this AE prime has discrepancy 1. Okay, I forgot to tell you. This is discrepancy 1 divisor, this one. And if we have another exceptional divisor, which has discrepancy 1, then its image on Y prime should be centered at one of these points. Because otherwise, it's easy to see that the discrepancy is higher, greater than 1. And it is then easy to see that there are only one, how to say, there are only one exceptional divisors centered at this half point with discrepancy smaller than 1. And so okay, we have one divisor over this point. So we have 2 points. So we have 2 divisors, and over this 1/4 point, we have 3 exceptional divisors. So in total, we have at most 1. This corresponds to E prime, plus 2 here, plus 3 here. So we only have 6 distinct exceptional divisors centered at this point. This is step 2. And step 3, then we construct 6 exceptional divisors with discrepancy 1 explicitly. Yes, how to do it. So we already have 1, this E prime. We already have 1. And we need to construct 5 more. And yes, so this P prime is the hypersurface singularity, of course. And okay, you don't have to take a look at this complicated equation. But anyway, we construct weighted blowups by looking at these equations. We construct weighted blowups, of course, at this point, P prime, and 5 distinct blowups by considering, of course, various weights, and possibly after doing some analytic coordinate change. Anyway, we construct weighted blowups, and with the following properties. So first, for any n, the exceptional locus of the blowup is a prime divisor. And next, okay, sorry, this is prime. The discrepancy is 1. And furthermore, this variety is a normal projective variety, of course, but it has singularity worse than terminal. So it's not in the terminal category. And finally, so we have 5 exceptional divisors of discrepancy 1, and together with E prime, we have 6. And yeah, these are all distinct as a valuation of the function field of X prime. Okay, so we explicitly construct these divisors. And finally, so here is a lemma by Kawakita. So this is a general lemma. So let GI be a projective birational morphism of normal varieties. So yeah, for I is 1 and 2, we have 2 such morphisms. And let EI be the exceptional locus of this birational morphism. And assume that yes, for each I, EI is a prime divisor, and minus EI is ample, GI ample. And the second, E1 and E2 are the same as valuations. Then G1 and G2 are isomorphic as morphism over X. So yes, together with this lemma and explicit construction of valuations, 6 valuations, and among these, this is the only one which corresponds to extremal divisorial contraction in of course in terminal category. So the other 5 go outside the terminal category. So these are not extremal divisorial contraction in terminal category. So as I explained, this shows this psi prime is a unique extremal divisorial contraction centered at this point. And sorry, go back to this slide. And we already have elementary links, the reverse elementary link initiated by this contraction. So we completely classified elementary link. And in this way, theorem 2 is completed. And this is how the proof is done. So I believe I can prove in the same way for the remaining families, but it is not done yet. So I stop here. Thank you very much.